Let us illustrate the procedure how to find minimum and maximum of a function of two variables by the following example. Consider the function fxy being x times y plus 50 over x plus 20 over y. First, it's a good idea to write the domain of definition. We have some fraction, so the denominator should be non-zero, and similarly for y, because it appears also in the denominator. Then we find the first order derivatives. F with respect to x is y minus 50 over x squared plus 0, and the derivative with respect to y is x minus 20 over y 0. Then we want to solve the equation, the system of equation fx is 0 and fy is 0. That means we have two equations, y minus 50 over x squared is 0 and x minus 20 over y squared is 0. In a general case, this may be a difficult task, a difficult step. For some equations, we are even unable to find the exact solution. Then we would have to use some approximate numerical method like the Newton method. But in this case, I hope we will find a solution. We can express y from the first equation, which is 50 divided by x squared, and we can substitute y into the second equation, and we have x minus 20 times, and 1 over y squared will be x to 4 divided by 50 squared. We can factor out x, and we have 1 minus 20 over 50 squared x cubed, and the product is 0 if this is 0 or this is 0. So we have one solution of this equation, y is 0, but this is not in the domain of definition of the function, independent of y. So this contradicts this equation. So this is not good. And if this bracket is 0, then x cubed must be 50 squared over 20, which is 250 divided by 2, 125. And this means x is cube root of 125, which is 5. And this is good. It is in agreement with this condition. And for x is 5, we can find a corresponding y, which is 50 divided by 5 squared, which is 2. So we have found that this function has a single stationary point, namely 2, 5. And to see whether there is a minimum, maximum, or a saddle, we evaluate the Hessian. So the second order derivative with respect to x, this is 0, and this gives x to minus 2 is minus 2x to minus 3. So we have 100 divided by x cubed. And fxy is 1, fyx is 1, and fyy is 40 divided by y cubed. this is the Hessian at the general point xy, and the Hessian at the stationary point 5, 2 is 100 divided by 125, 40 divided by 8, which is 405, 115, which is 4 minus 1, which is 3. This is positive. That means we have some extremum. And if we look at this derivative, this is positive, so we know that the point is minimum. And we can evaluate the function at the point 5, 2, which will be 10 plus 10 plus 10. So this function has a single stationary point, and this is the minimum at the point 5, 2 equal to 30.